3 billion miles away, a planet is doing something that should be impossible. Neptune, the farthest planet in our solar system, just lost its clouds, flipped its temperature in 2 years, and sent a continent-sized storm running in the wrong direction. Scientists built models for decades. Every single one got it wrong. Tonight we go to the edge of the solar system, into supersonic winds, disappearing skies, and storms that smell like rotten eggs. If you enjoy the journey, subscribe and keep watching. Prepare yourselves. We begin. 3 billion miles away, something is changing, and nobody saw it coming. Neptune sits at the very edge of our solar system. If you drove there at highway speed without stopping, the trip would take about 3,000 years. The planet is so far out that sunlight takes more than 4 hours just to reach it. By the time that light arrives, it is about 900 times weaker than what you feel on a summer afternoon. For most of human history, Neptune was just a faint blue smudge in a telescope. Scientists knew it existed, tracked its orbit, and made educated guesses about what was happening on its surface. Those guesses seemed reasonable. The planet was cold, distant, and slow-moving. Surely it followed predictable rules. Then the numbers started coming in. Starting in 2003, a group of astronomers began doing something that had never been done before. They pointed a series of powerful ground-based telescopes at Neptune and started measuring its atmospheric temperature on a regular basis. Year after year, the same planet, the same measurements. The goal was simple: build a long-term record so scientists could actually understand how this distant world behaves over time. What they got instead was a slow-building alarm. The first few years looked normal enough. Temperatures matched what the models predicted. Scientists felt confident. Neptune was entering its southern summer, a season that lasts over 40 Earth years, because the planet takes 165 years to complete a single orbit around the Sun. During summer, temperatures were expected to gradually rise. That is basic physics. Point a hemisphere toward the Sun and it warms up. Every planet does it. Neptune did the opposite. Between 2003 and 2018, the global temperature of Neptune's atmosphere dropped by 14 degrees Fahrenheit. That is not a small reading error or a seasonal wobble. 14 degrees across an entire planet, over 15 years, while that planet was supposed to be warming up. Scientists stared at the data and checked it again. The instruments were fine. The readings were consistent. The drop was real. To put that in perspective, 14 degrees is the difference between a warm spring afternoon and a freezing winter morning. Imagine the entire Earth suddenly getting 14 degrees colder with no explanation. No volcano, no asteroid, no change in the sun. Just a number on a screen getting lower, year after year. Scientists had no model that predicted this. The cooling broke the rules. And here is what made it stranger. The sun was still shining on Neptune's southern hemisphere. The planet had not moved away from its star. Nothing in the outer solar system had changed. The cooling happened for reasons that existed entirely within the planet itself, somewhere deep in its chemistry or its energy system, somewhere humans have never been and cannot yet see. Some researchers suggested chemical changes in the atmosphere were altering how the planet releases heat into space. Others pointed to shifts in the way Neptune's internal energy moves through its layers. Nobody could agree. Nobody had proof. What they did agree on was the obvious question that came next. If the planet dropped 14 degrees for no known reason, what else was it capable of doing? The answer came 2 years later, and it was worse. Neptune's seasons are unlike anything on Earth. Here, a season lasts about 3 months. You get used to the rhythm. Summer comes, temperatures rise, leaves grow. Winter comes, temperatures fall, everything slows down. You can plan around it. You can predict it. On Neptune, one season lasts longer than 40 Earth years. That means a child born at the start of a Neptunian summer would grow old and die before that summer ever ended. The planet moves so slowly around the Sun, tracing its giant loop through deep space, that the idea of seasonal change barely applies in any human sense. Scientists use this extreme timescale to make predictions. If a season lasts 40 years, changes inside it should be gradual, slow, spread across decades. A planet does not flip its temperature inside a single season the way you flip a pancake. Physical systems that large carry enormous momentum. Changing them takes time. That made what happened between 2018 and 2020 so difficult to accept. Neptune's southern summer had officially started around 2005. For the first dozen years, temperatures were already dropping in the global atmosphere, which was puzzling enough. But at the South Pole specifically, something different was building, and in 2018 it released. In just 2 years, the temperature at Neptune's south pole spiked by 20 degrees Fahrenheit, 20 degrees, in 2 years, on a planet where seasons stretch across 4 decades. To understand how violent that is, picture a frozen lake in January. Now imagine the entire lake turns into a boiling hot spring by March. The speed of the change is the terrifying part. Physical systems, the size of a planet, are supposed to resist sudden shifts. They have too much mass, too much atmosphere, too much inertia. A 20-degree spike in 2 years on a planet Neptune's size is the equivalent of a mountain range deciding to move overnight. No planetary model predicted this. Scientists had equations for how ice giants handle heat. They had formulas built on decades of observation. The south pole of Neptune tore through every single one of them. The global atmosphere was getting colder. The south pole was getting hotter. Both things were happening at the same time, on the same planet, during the same season. These two movements were going in completely opposite directions. That should not be possible under normal atmospheric physics. Heat is supposed to spread out and balance. Warm air rises and mixes. Cold regions and hot regions exchange energy until things even out. Neptune's atmosphere seemed to be doing the opposite of evening out. It was splitting. Researchers scrambled for explanations. One idea was that ultraviolet light from the sun was hitting the South Pole at just the right angle to trigger localized chemical heating. Another suggestion was that Neptune's internal heat, which the planet generates on its own from deep inside, was escaping unevenly through the polar region. Both ideas had some support. Neither had proof. What scientists did know was this: 2 simultaneous and contradictory temperature events happening during the same season meant their understanding of ice giant physics was fundamentally incomplete. The planet was behaving like something they had never studied before. And then, a year later, they looked up at Neptune through their telescopes and realized the sky itself had changed. For 30 years, Neptune had clouds, bright, white, constantly shifting bands of cloud stretched across the planet's face. They were one of the first things astronomers pointed to when describing Neptune as a dynamic, active world. The clouds were visible from Earth through powerful telescopes, and they confirmed that something energetic was happening in the planet's atmosphere. They moved, they changed shape, they were real, and they were always there. Then, in October of 2019, they were gone. Telescope after telescope confirmed it. The vivid cloud bands that had defined Neptune's appearance for 3 decades had almost completely disappeared. The entire planet, which used to look like a swirling blue marble, full of texture and activity, became something else entirely. A smooth, nearly featureless blue sphere, like a cue ball floating in space. Only one tiny wisp of cloud remained visible, drifting quietly near the extreme southern pole. Scientists who had studied Neptune for their entire careers stared at the images and felt something close to disorientation. The planet still existed. Its gravity and orbit were unchanged, but its atmosphere had gone visually silent in a way that felt wrong in a deep, unshakable way. Understanding what happened requires knowing what Neptune's clouds actually are. On Earth, clouds form when water vapor cools and condenses into tiny droplets. Simple enough. On Neptune, the process is completely different. The planet's upper atmosphere contains chemicals including methane and hydrogen sulfide. When ultraviolet light from the sun hits these chemicals, it triggers a series of reactions that build a kind of photochemical smog, a hazy, frozen layer of particles that sits high in the sky and forms the bright cloud bands we see from Earth. No ultraviolet light, no reaction. No reaction, no clouds. And this is where the story gets genuinely strange. Scientists started looking at data from the sun. Specifically, they looked at the 11-year solar cycle, the regular pattern in which the sun's activity rises and falls, pumping out more or less ultraviolet radiation depending on the phase. The correlation was striking. When solar activity dropped to its minimum, Neptune's cloud coverage decreased. When solar activity rose, the clouds came back. The connection seemed real, and it stretched across 2 decades of observations. The sun, nearly 3 billion miles away, was reaching across the solar system and turning Neptune's clouds on and off like a light switch. But this created a new and uncomfortable problem. If the clouds are tied to the solar cycle, they will eventually return. Scientists are watching and waiting for that to happen as the sun's current cycle ramps back up. But the clouds are only one piece. The disappearance alone cannot explain the temperature swings, the polar heating, or the reversing storms. The clouds vanishing was a symptom. Something deeper was driving all of it. And that something deeper had been hiding in plain sight for years, churning beneath Neptune's smooth blue surface, building pressure, generating heat, and occasionally punching enormous dark wounds into the sky. Those wounds had a name, and the next one was already forming. Neptune grows storms bigger than entire oceans. The dark vortices that appear on Neptune's surface are massive high-pressure systems. Scientists classify them as storms, but that word barely captures what they are. The largest ones stretch wide enough to cover the entire Atlantic Ocean from the coast of North America all the way to Europe. Lay one over the eastern half of the United States, and it would swallow every state east of the Mississippi River and keep going. These storms are dark because of what is inside them. The vortex itself pulls up material from deep within the atmosphere, particles and chemical compounds that absorb light rather than reflect it, turning whole regions of the sky into shadowy, light-eating patches. From Earth, they look like bruises on the planet's face. Scientists first observed a large, dark vortex in 1989 when Voyager 2 flew past Neptune. That storm was called the Great Dark Spot, and it was roughly the size of the entire Earth. By the time Hubble pointed at Neptune a few years later, that specific storm had vanished completely. A new one had formed near the North Pole. Then that one faded too. For years, researchers developed a model to explain the life cycle of these storms. Dark vortices form at middle latitudes, the region between the poles and the equator. They grow, drift slowly toward the equator, and then die. The equator kills them. Wind patterns there create intense shear, forces that tear the storm apart from the inside, the way a river current shreds a leaf. The model was clean. The model made sense. Then one storm decided to stop following the model. In 2015, Hubble spotted a new dark vortex in Neptune's northern hemisphere. Researchers watched it with interest, expecting the familiar drift toward the equator and the predictable death that followed. The storm moved as expected at first, sliding southward at a pace consistent with previous observations. And then it turned around. Instead of continuing toward the equator and the destruction waiting there, the storm reversed course and started moving back toward the northern polar region. Scientists watching the data had to verify it multiple times. Storms on this scale carry enough momentum and energy that reversing direction requires an enormous force pushing back against the original motion. Something inside Neptune's atmosphere had hit that storm hard enough to send it retreating. The storm survived because of the reversal. Away from the equatorial shear, it had room to exist. It kept spinning. It kept growing. Nobody had ever seen this before on any planet. The reversal shattered the tidy model scientists had used for decades. If storms could choose a different path, if something inside Neptune's atmosphere could redirect a system the size of an ocean, Then the rules governing the planet's interior were far more complex than any existing theory described. Researchers began asking a new question. The storm reversed course because something pushed it. What was doing the pushing? The answer, when it started coming together, pointed somewhere scientists had not expected. Deep inside the planet, far below any layer Voyager ever reached, something was moving, and that movement was leaving marks on the surface that nobody could fully explain. Those marks were about to get weirder. The storm reversed course, and then something even stranger broke off from it. As scientists tracked the dark vortex making its surprising retreat toward Neptune's north pole, Hubble captured something new forming nearby. A smaller, bright companion spot had appeared right next to the main dark storm. It was glowing in the red part of the light spectrum, hovering at the same altitude as the dark vortex, traveling alongside it like a satellite. Researchers called it a dark spot companion, and they had a working idea about what it might be. When a massive vortex spins through the atmosphere, it can shed material from its outer edge, the way a spinning top flings water off its surface. The companion was possibly a fragment, a piece of the original storm that had broken free and was now drifting independently. But the companion behaved in ways that a simple fragment should not. It persisted, it held its shape, it continued emitting that distinctive red spectrum light over multiple observations. Fragments of storms typically disperse quickly, torn apart by the winds around them. This one stayed together, which suggested it had its own internal structure, its own driving force. Scientists who studied the companion noted that the red wavelength light was significant. Certain chemical compounds in Neptune's atmosphere reflect light in that part of the spectrum. Methane, ice, and some forms of hydrogen compounds can produce that signature. The companion was potentially rich in one of those materials, pulled up from a deeper layer of the atmosphere and compressed into a coherent structure by the spinning vortex that created it. Here is what makes this genuinely unsettling. If material from deep inside Neptune can travel upward, get compressed by a storm, break off as a stable fragment, and persist for weeks or months at high altitude, that means the planet's internal layers are far more connected to its surface behavior than the models ever suggested. The skin of the planet is talking to the deep interior, and the conversation is chaotic. While all of this was happening in the northern region, a separate team using the Very Large Telescope in Chile was observing the southern hemisphere. They found something waiting there too. A brand new dark spot had appeared, this one in the south, alongside its own bright companion. Two different storm systems on opposite sides of the planet, each with a dark vortex and a bright partner, both active at the same time. Planetary scientists had never recorded that before. Two simultaneous paired storm systems on a single planet. The pace of new anomalies was accelerating. Each observation brought a new discovery that raised more questions than it answered. The temperature swings, the vanishing clouds, the reversing storms, the bright companions, the simultaneous events on opposite hemispheres. These were not separate incidents. They were symptoms of a single, massive, ongoing process inside Neptune that scientists could not yet see clearly. There was one more thing the telescopes picked up during this period. Something happening to other storms on the planet. Storms that had nothing to do with the reversing vortex or the bright companions. These were separate systems, previously stable, minding their own atmospheric business, and they were dying at a speed that made no sense at all. Some storms on Neptune do not get to reverse course. They simply get destroyed. While researchers were tracking the reversing dark vortex and its bright companion, other telescope teams were watching different storm systems across Neptune's atmosphere. These were smaller vortices, separate from the famous reversing storm, active in their own regions of the planet. Scientists expected them to follow the known life cycle, form, drift, fade slowly over months or years. Instead, some of them collapsed in days. A storm system that had been stable and visually distinct for weeks simply shrank and disappeared over the course of a few observations. The speed of the collapse left researchers struggling to find a cause. Planetary storms on this scale carry enormous energy. Draining that energy fast enough to kill the storm in days requires a force of equal or greater power working against it. That force is wind shear. Wind shear is what happens when two layers of atmosphere moving at different speeds collide with each other. Picture two rivers flowing side by side. One moves fast, one moves slow. Where they meet, the water churns and twists violently. Now imagine that happening in the atmosphere, with layers of gas moving at hundreds of miles per hour in opposite directions. Any storm structure caught in between gets grabbed on both sides and pulled apart. On Earth, wind shear is the reason hurricanes weaken when they move over land or hit certain atmospheric layers. The storm loses its organized spin, it falls apart. On Neptune, the wind shear operates on a scale that has no comparison on our planet. Neptune's winds are the fastest in the solar system. Near the equator, wind speeds reach around 1,200 miles per hour. That is faster than the speed of sound. A passenger jet cruises at around 550 miles per hour. Neptune's equatorial winds move more than twice that fast. When a storm drifts into a region where different atmospheric layers are moving at those kinds of speeds in opposite directions, the result is instant destruction. The storm does not weaken gradually, it gets shredded. What surprised scientists was how quickly some of these collapses happened in the recent observation period. Earlier models suggested storms would survive longer at certain latitudes before encountering the worst shear zones. The new data showed storms dying faster and at locations where the models did not predict such violent shear activity. This meant the internal wind structure of Neptune was different from what every existing model described. The shear zones were in new places, or more intense than expected, or moving. The atmosphere was rearranging its own danger zones. And here is the part that makes this relevant beyond Neptune. Every planet with an atmosphere has wind shear. Earth has it, Saturn has it, Jupiter has it. The models scientists use to predict atmospheric behavior on all of these planets share the same basic physics. If those models are getting Neptune's shear zones wrong, researchers have to ask what else the models are getting wrong. Neptune was beginning to look like a test case that exposed flaws in the entire system of atmospheric science. But the storms and the shear were only describing the surface of the problem. Beneath Neptune's blue shell, something was generating heat on its own, independent of the sun, for reasons that nobody fully understood. And that internal heat engine was the engine driving everything above it. Something down there was running hot, and it had been for a long time. Neptune makes its own heat, and scientists are still not sure exactly how. Every planet in the solar system receives energy from the sun. That is expected. The closer you are, the more you get. Neptune, sitting nearly 3 billion miles from the sun, receives only a tiny fraction of the sunlight Earth does. On a scale from 1 to 100, Earth gets about 100 units of solar energy. Neptune gets roughly 1 unit, maybe slightly more, and yet Neptune is warmer than it should be for a planet that far out. Here is the key detail. Scientists measure two things: how much solar energy a planet absorbs, and how much energy the planet radiates back out into space. For a planet in thermal balance, those two numbers match. Energy in equals energy out. Neptune's numbers do not match. The planet consistently radiates more energy out than it receives from the sun. The extra heat has to come from somewhere, and that somewhere is deep inside Neptune itself. This is called internal heat generation, and it is a known phenomenon on some planets. Jupiter does it too. The leading explanation involves leftover heat from the planet's formation. When a planet forms, enormous amounts of material collide and compress together, and that compression generates heat. Some planets hold that original heat for billions of years, slowly leaking it out into space. Neptune may still be releasing energy from its birth nearly 4.5 billion years ago. Another explanation involves something happening inside Neptune's core right now. At the extreme pressures found deep inside an ice giant, some scientists believe that carbon atoms get crushed so hard they crystallize into diamonds. Actual diamonds. falling like rain through the interior of the planet, sinking toward the core as they form. As the diamonds fall and the surrounding material shifts, that movement generates heat, a diamond rainstorm powering a planet's internal furnace. That idea sounds impossible. Multiple experiments using high-powered lasers to recreate those extreme pressures have shown it is physically real. The diamonds form. Whether Neptune's internal heat comes from ancient compression, diamond rain, or some other process still being studied, the result is the same. The planet has its own power source, and it operates below any layer a telescope or probe has ever reached. And here is why this matters for everything else happening on Neptune right now. If the internal heat source changes, even slightly, the effects ripple all the way up through the atmosphere. Changes in how heat moves through the planet's layers could alter wind patterns, shift temperature distributions, destabilize cloud chemistry, and redirect storm systems. Everything seen in Neptune's atmosphere since 2003, the cooling, the polar spike, the vanishing clouds, the reversing storms, could be connected to changes happening miles below the surface, in a region no instrument has ever directly measured. Scientists know the heat is there. They know it is uneven. They know it can change. What they do not know is exactly what drives it, and whether what is happening right now is a temporary fluctuation or something more permanent. And then there is one more layer to this mystery that makes even the internal heat question feel manageable by comparison: the dark particles. The ones that appear inside the storms and cannot be explained. Where do they actually come from? The storms on Neptune are dark for a reason. Scientists just cannot agree on what that reason is. When a dark vortex appears on Neptune's surface, the defining feature is obvious from the name. The area inside the vortex absorbs light. Where the rest of the planet reflects blue light back toward our telescopes, the dark spot swallows it. The result is a shadowy, bruise-colored patch cutting across the bright blue atmosphere. For years, scientists assumed the dark appearance was simply the result of the vortex pulling up material from below the cloud layer, exposing a deeper, darker region of the atmosphere that normally stays hidden. Simple enough. The storm acts like a vacuum, pulling the curtain back on something underneath. But that explanation does not hold up under close examination. The dark material inside these vortices does not behave like a simple layer that got exposed. It has its own structure. It evolves. It changes density and distribution over time in ways that suggest it is composed of specific particles with their own chemical identity, something active rather than just a passive backdrop. A team of researchers studying the most recent dark spot used instruments capable of breaking light into its individual color components, which reveals what chemicals are present in the target area. What they found was surprising. The dark material appeared to contain hydrogen sulfide, the same chemical responsible for the rotten egg smell that makes Neptune's atmosphere famous in science discussions. But the particles were in a form and at an altitude where they should not have been able to survive. Hydrogen sulfide ice typically exists deep in Neptune's atmosphere, under enormous pressure. At high altitude, where these dark spots float, the pressure is too low, and the temperature is too variable for that material to remain stable. Something was carrying it upward and holding it together long enough to form a visible, persistent patch of darkness. The vortex itself might be the answer. A powerful enough spinning system could lift deep atmospheric material up through multiple layers and compress it at altitude, locking it into a structure it would never naturally occupy. The storm becomes a kind of elevator, hauling chemical cargo from the deep and pinning it to the surface of the atmosphere. But there is a competing idea that several researchers find more compelling, and it is harder to test. Some scientists believe the dark particles are not hydrogen sulfide at all. They suggest the material is something currently unidentified, a compound or mixture that forms exclusively under the extreme conditions inside Neptune's vortices and has no parallel anywhere else in the solar system. An unknown substance, created inside a storm, on a planet humans have never visited in person. If that is true, Neptune is carrying chemistry in its atmosphere that our periodic table and our lab experiments cannot yet describe. And the only way to know for certain is to go there, send a probe directly into one of those storms, and bring back a sample. No such mission exists yet. The probe idea raises its own terrifying set of questions. Getting a spacecraft into Neptune's atmosphere requires surviving conditions that would destroy most hardware within seconds. The winds alone, moving at over 1,000 miles per hour, would be the first problem, and they would be far from the last. Humanity has visited Neptune exactly once. In the summer of 1989, Voyager 2 swept past Neptune after a 12-year journey from Earth. The spacecraft came within about 3,000 miles of the cloud tops, close enough to capture the first detailed images of the planet's storms, rings, and moon system. Scientists got roughly 5 hours of close-range data. Then Voyager 2 kept moving, heading out of the solar system, never to return. That 5-hour window is still the primary source of direct information about Neptune. Everything observed since then comes from telescopes on Earth or in orbit, pointing across billions of miles of space. Even Hubble, the most powerful space telescope humans have ever built, is seeing Neptune from a distance that makes any fine detail nearly impossible to capture. And the planet is changing faster than those distant instruments can fully explain. Scientists have been pushing for a dedicated Neptune mission for decades. The scientific case is overwhelming. An ice giant probe would answer questions about planetary formation, atmospheric chemistry, internal heat generation, and the behavior of storms that no existing model can resolve. Ice giants make up the majority of planet types discovered in other solar systems. Understanding Neptune means understanding a category of worlds that appears to be one of the most common in the universe. The engineering challenges are severe. Getting a spacecraft to Neptune takes a long time. Voyager 2 needed 12 years. With modern propulsion and gravity assist techniques, a well-designed mission could potentially arrive in 10 to 12 years. But that still means launching a spacecraft today and waiting until the late 2030s to start collecting data. Once there, actually entering the atmosphere requires a heat shield that can withstand enormous temperatures generated by atmospheric entry at high speed. The probe would be moving fast enough that friction with Neptune's outer atmosphere would create temperatures rivaling the surface of the Sun for a brief, violent few minutes. After surviving that, the probe would face the wind shear, atmospheric pressure, and chemical environment of a world that has never been directly sampled. The probe would likely survive for less than an hour before the pressure and temperature crushed it completely. 1 hour. For the first direct atmospheric measurements of the most mysterious planet in the solar system, scientists consider that an acceptable trade, 1 hour of direct data from inside Neptune's atmosphere, would transform understanding of ice giants the same way a single deep ocean dive transformed understanding of Earth's oceans. The brief window changes everything. A formal proposal for a Neptune orbiter and probe was placed high on the priority list by planetary scientists in the most recent 10-year survey, a report produced every decade to guide where space agencies focus their resources. The recommendation was clear. The support was real. The mission has not been funded yet. Budget constraints, competing priorities, and the long development timelines have kept a Neptune mission on the wish list rather than the launch pad. Every year without a mission is another year of watching Neptune change from a distance and making educated guesses about the causes. And while humanity waits for that mission to become real, Neptune keeps running its own experiments. Storms forming, temperatures swinging, clouds vanishing, and potentially returning. A planet-sized laboratory with no scientists inside it. The most recent experiment involves the Sun, and the connection between a star 93 million miles from Earth and a planet nearly 30 times farther out is stranger than it first appears. The Sun controls Neptune's clouds from nearly 3 billion miles away. That sentence should feel strange. The Sun is so far from Neptune that its light takes over 4 hours to arrive. By the time solar energy reaches the outer solar system, It has spread so thin that a solar panel on Neptune would produce almost nothing. The planet sits in a region of space where the Sun looks like a slightly brighter star rather than the blazing disk we see from Earth. And yet, somehow, the Sun is responsible for Neptune's cloud system. The connection runs through chemistry. Neptune's upper atmosphere contains a mixture of gases, primarily hydrogen, helium, and methane. When ultraviolet radiation from the Sun hits methane molecules in that upper layer, it breaks the molecule apart. The fragments then react with each other and with surrounding gases, creating new compounds. These new compounds freeze at Neptune's extreme temperatures and form tiny ice particles that group together into the hazy cloud bands visible from Earth. Scientists call this process photochemistry, light-driving chemical reactions, and it is entirely dependent on how much ultraviolet radiation is arriving from the Sun at any given time. Here is where the 11-year solar cycle enters the story. The Sun is not a steady, unchanging light source. It cycles through periods of high activity and low activity, roughly every 11 years. During high activity, the Sun produces significantly more ultraviolet radiation. During low activity, that output drops. A team of researchers comparing decades of Neptune cloud observations against the solar cycle found a striking match. The cloud coverage on Neptune rose and fell in step with the solar cycle, with a slight delay of about 2 years. The delay makes sense. Photochemical reactions take time to produce visible clouds, and the process of building or dismantling cloud structures happens gradually. When the Sun went through a low activity phase around 2019, ultraviolet output dropped. The chemical reactions slowed, and Neptune's clouds faded almost entirely. The planet turned into that smooth blue sphere. Now the Sun is heading back toward a high activity period. Researchers watching Neptune are waiting to see if the clouds return on schedule. If they do, it confirms the solar cycle connection in a powerful way. But here is the uncomfortable part. Even if the clouds come back exactly on cue, that still does not explain the temperature swings. The solar cycle cannot account for a 14-degree global cooling or a 20-degree polar spike. The Sun's ultraviolet changes are real, but too small to drive that kind of thermal violence. Something else is doing that. Something that operates on a different timescale, responds to different inputs, and connects the deep interior of Neptune to its visible surface in ways that the solar cycle theory cannot touch. Scientists suspect that deep interior processes and solar influences are running simultaneously on Neptune, layering their effects on top of each other in a way that makes both of them harder to separate and understand. Two different forces, one planet, both pushing the atmosphere in different directions at the same time. And the result, when both forces align, might be something far more extreme than what scientists have already observed. What the data suggests about Neptune's future behavior is something researchers have been reluctant to say out loud. Neptune is blue. That simple fact hides one of the strangest stories in planetary science. The color comes from methane. When sunlight reaches Neptune's upper atmosphere, methane gas absorbs the red wavelengths of light and reflects the blue ones back into space. The result is that brilliant, deep blue color visible in every photograph of the planet. It is beautiful. It is also a mask. That blue color makes Neptune's surface look calm and uniform, a smooth, glowing sphere hanging in the dark. When the clouds vanish and the planet becomes featureless, the blue deepens even further, and the planet looks even more peaceful from a distance. But the color tells you almost nothing about what is actually happening. All the chaos, the temperature swings, the reversing storms, the dark particles, the internal heat engine, everything happening on this planet occurs either beneath the visible blue layer or within structures so dynamic they are difficult to track from billions of miles away. The blue is a curtain. Methane itself is worth understanding because it plays so many roles at once on Neptune. It colors the planet. It reacts with sunlight to build clouds. It mixes with other gases at depth to form compounds whose properties scientists are still mapping. And it is part of the chemical chain that creates the hydrogen sulfide responsible for the rotten egg smell that permeates the storm systems. Think of methane on Neptune like a single ingredient that shows up in every dish in a restaurant. Pull it out, and the entire menu changes. Scientists also use methane as a tracer. By watching how methane distributes itself across different atmospheric levels, they can infer where vertical movement is happening, where material from deep inside the planet is pushing upward, and where the atmosphere is sinking and compressing. Methane mapping is one of the few tools available for understanding the invisible interior without actually going there. What those maps have shown in recent years is deeply unsettling. The vertical movement of material in Neptune's atmosphere has been more active than expected. Regions that should be relatively calm are showing signs of significant upwelling, material pushing up from depth, and those upwelling zones correlate with where the dark spots appear. The planet is bringing its interior to the surface. Slowly, chaotically, in massive bursts that create storms and dark spots and temperature spikes. And the blue surface reflects all of it back into space, looking serene while it does. There is something almost deceptive about it, a planet that looks quiet from the outside while running violent, unresolved processes on the inside. Scientists have a phrase for this kind of object. They call it a dynamic system in apparent equilibrium, a system that looks stable but is actually churning. Neptune, in 2019, dropped even the appearance of equilibrium. The clouds vanished, the blue deepened, the illusion of calm became almost total, and then the dark spots came back anyway. Beneath the smooth blue surface, the vertical movement was still happening. The deep chemistry was still working. The internal heat was still looking for a way out, and when it found one, it punched straight through the blue curtain and made itself visible. What those dark spots are made of at the molecular level is one question. What they are doing to the atmosphere around them is another question entirely. A dark spot on Neptune does not just sit there, it reshapes the atmosphere around itself. When a vortex forms and locks into a spinning structure, the rotation creates pressure gradients. High-pressure air sits at the center of the dark spot. Around the edges, the spinning motion drags neighboring atmospheric gas into patterns that affect temperature, chemistry, and wind speed across a wide area. On Earth, a hurricane does something similar. The storm itself occupies a certain area, but the bands of rain and cloud extend for hundreds of miles in every direction. The storm organizes the atmosphere around it, creating structures that exist purely because of the storm's presence. Neptune's dark vortices do this on a much larger scale. A vortex that stretches 3,000 miles across, similar in width to the entire continental United States, produces gravitational and pressure effects that extend well beyond its visible edges. The surrounding atmosphere responds to the vortex the way metal filings respond to a magnet, organizing into bands and structures that otherwise would not exist. One observed effect is temperature variation in the rings around the vortex. Researchers have found that the air immediately surrounding some dark spots runs warmer than the air further away. The vortex draws energy from the atmosphere around it, and in doing so, creates a warm halo. That warm halo can alter cloud chemistry in the surrounding region, either promoting cloud formation or suppressing it depending on the specific conditions. A second effect involves the distribution of chemical compounds. The spinning vortex acts as a centrifuge. Materials of different densities separate as they spin, with heavier particles moving outward and lighter ones concentrating toward the center. This sorting mechanism means the chemistry at the center of a Neptune vortex is different from the chemistry at its edges, which is different again from the surrounding undisturbed atmosphere. And a third effect, still poorly understood, involves how the vortex interacts with Neptune's internal heat. Some researchers have proposed that the spinning structure creates a channel, a pathway through the atmospheric layers that allows heat from deep inside the planet to travel upward more efficiently in certain locations. The vortex punches a hole in the insulating layers above the interior, letting heat escape in a concentrated stream. If this is happening, it means the dark spots are not just symptoms of internal activity, they are accelerators of it. The The storm makes it easier for more heat to escape, which alters the atmosphere further, which potentially creates conditions for more storms. A feedback loop. Neptune feeding itself. This is a concept that makes atmospheric scientists uncomfortable because feedback loops in planetary systems can be difficult to predict and difficult to stop. If Neptune's dark vortices are actively accelerating the internal heat release, the planet could be in the early stages of a long-term shift in its overall energy balance. Or the fluctuations could be temporary, part of a cycle that eventually reverses. Scientists cannot yet tell which scenario is more likely. What they can tell is that every new observation adds something unexpected. The planet is not settling into any predictable behavior, and the longer they watch without a direct probe, the more questions pile up. The strangest of those questions is one that researchers have been thinking about since the very first temperature drop was recorded. If Neptune is changing this fast, and if internal processes are driving the change, then something must have triggered those internal processes to shift. Something changed inside Neptune. What was it? Scientists can see the effects at the surface. They cannot see what started it. The temperature dropped. The polar regions spiked. The clouds vanished. The storms reversed. The dark particles appeared. Each of these events is visible from Earth, measurable with instruments, and documented across years of observation. The trail of symptoms is clear. What remains hidden is the origin. The thing inside Neptune that shifted and sent all of these effects rippling up through the atmosphere to the surface. Scientists have a few serious hypotheses. Each one has evidence in its favor. None of them has been confirmed. The first hypothesis centers on heat redistribution. Neptune generates its own heat from deep inside, and that heat is not uniform across the planet. Some regions of the interior are hotter than others. If the distribution of that heat changes, if a region that was previously cooler starts running hotter or a previously stable zone becomes more active, the effect on the atmosphere above it could be dramatic. A shift in interior heat patterns could simultaneously cool one part of the atmosphere while warming another, which is exactly what the data shows happening between the global cooling and the South Pole spike. The second hypothesis involves the behavior of exotic materials under extreme pressure. At the depths inside Neptune, pressures are so intense that water, ammonia, and methane stop behaving the way they do on the surface. They enter a state scientists call superionic, where the molecules partially dissolve and the material conducts electricity like a metal while still flowing like a liquid. Changes in how these superionic layers circulate could alter how heat moves through the planet and how it eventually escapes. A shift in superionic circulation deep inside Neptune could produce atmospheric effects years or even decades after the interior change began. This is called a delayed response, where the cause and the visible effect are separated by so much time and distance that connecting them directly is nearly impossible. The third hypothesis is the most speculative, but has attracted genuine scientific attention. Some researchers have proposed that Neptune is currently adjusting its internal structure in response to forces that have been building over millions of years. Long-term changes in orbital dynamics, the gravitational influence of other planets, and the slow settling of the planet's internal layers could all contribute to a kind of deep structure reorganization, a planet settling itself, like a building shifting on its foundation, but happening over timescales humans can barely imagine. None of these three hypotheses is mutually exclusive. All of them could be contributing simultaneously, layering their effects and making the overall picture impossible to untangle without data from inside the planet itself. And here is the thing that keeps some planetary scientists up at night. If the cause is internal, and if it is gradual and ongoing, then what humans have seen since 2003 might only be the beginning. The changes could continue accelerating, the atmosphere could shift further, the storms could grow larger and more frequent, or everything could reverse tomorrow and settle back to the patterns Voyager saw in 1989. Both outcomes are scientifically possible. Both outcomes are equally uncertain. and the only way to know which direction Neptune is heading is to send something there to look. The scientists making that argument are doing so louder now than they were 10 years ago, because something about recent observations has changed the level of urgency in the conversation. The scientific community does not panic easily. Researchers spend careers making careful observations, writing cautious papers, and qualifying every conclusion with phrases about uncertainty and the need for further study. It is a culture built on restraint, on skepticism, on waiting for more data before drawing strong conclusions. So, when planetary scientists started using words like unprecedented and deeply puzzling and unlike anything in our models, the field paid attention. The pace of anomalies on Neptune since 2003 has no parallel in the history of planetary observation. No other planet in the solar system has shown this many simultaneous departures from expected behavior in such a short window of time. One anomaly gets studied and explained. A pattern of simultaneous, connected, and escalating anomalies is a different kind of scientific problem. What changed the conversation most sharply was the 2019 cloud disappearance. Before that event, the temperature swings and storm reversals were serious concerns. Researchers were publishing papers, presenting at conferences, and arguing about possible causes, but the discussion stayed within the bounds of normal scientific discourse. New data, new models, revised predictions. The cloud disappearance was different. Clouds had been present on Neptune for the entire span of human observation of the planet. The first images from Voyager in 1989 showed clouds. Every decade of subsequent telescope observation showed clouds. They were a defining feature of the planet, assumed to be as permanent as the blue color itself. When they vanished in a matter of months, it was a visible demonstration that Neptune was capable of changes far faster and more complete than any model had allowed. An entire planetary cloud system gone, and it was gone for years. As of 2023, some researchers reported faint signs of cloud reformation beginning, but the original cloud coverage has not fully returned. The planet that Voyager photographed in 1989 does not currently exist. It has been replaced by something different. This raised an uncomfortable question that planetary scientists do not have a clean answer to. Is Neptune returning to its previous state, or is it moving toward a new one? Planets can have stable states, conditions that persist for millions of years because the physics that maintains them is robust. If Neptune is transitioning from one stable state to a different stable state, the planet might look fundamentally different 100 years from now than it did 100 years ago. That idea has enormous implications for how scientists think about planetary evolution. If a planet can shift its atmospheric chemistry, cloud coverage, and storm behavior on human timescales rather than geological ones, then the notion that planets are slow, stable, and predictable requires serious revision. The solar system is more dynamic than the textbooks suggest, and Neptune is proving it. The loudest voices now are the ones calling for a dedicated Neptune mission. Every year, without one, is another year of watching from a distance, while the planet changes in ways that are outpacing the models. But there is one more dimension to this story that makes even the mission argument feel small by comparison, because Neptune is not unique. There are billions of planets in the galaxy that belong to the same category, ice giants. And what happens on Neptune might be happening on all of them. Most planets in the galaxy probably look like Neptune. That is one of the central findings from the past 2 decades of telescope surveys aimed at other solar systems. Astronomers have catalogued thousands of planets orbiting other stars, and the most common category, by a significant margin, is worlds similar in size and type to Neptune and Uranus. Scientists call them ice giants, and they turn up constantly in the data from distant star systems. Gas giants like Jupiter and Saturn are dramatic and well studied. Rocky planets like Earth and Mars are the focus of most public attention. Ice giants sit in between, physically and conceptually. They are larger than Earth but smaller than Jupiter. They have thick atmospheres made of chemicals like methane, water, and ammonia rather than pure hydrogen and helium. They generate their own internal heat. They have complex weather systems, and in our own solar system, they are the least understood category of planet by a wide margin. Humanity has sent multiple missions to Jupiter and Saturn. We have studied their atmospheres, mapped their moons, and built detailed models of their interiors. Voyager 2 gave us 5 hours at Neptune. The scientific gap between what we know about gas giants and what we know about ice giants is enormous. This matters because every exoplanet discovery survey is pointing at ice giants and saying these are everywhere. They are the default planet. When a solar system forms around a star, the most likely outcome appears to be a collection of rocky inner worlds and icy outer worlds of roughly Neptune's size. Earth is the rare exception. Jupiter is the dramatic exception. Neptune is the template. So when Neptune starts behaving in ways that break every existing model, it is not just a local curiosity. It is a warning about how little we understand the most common kind of planet in the universe. Every atmospheric model, every interior simulation, every theory about how ice giants maintain stable climates and weather systems, all of it is built on observations of a planet that is now telling us the model is wrong. If those models are wrong for Neptune, they are probably wrong for the thousands of ice giants astronomers are trying to characterize in distant solar systems. Scientists studying the atmosphere of a planet 400 light-years away are using the same physics they use to model Neptune. If that physics cannot explain what is happening in our own backyard, the exoplanet conclusions need to be revisited. This is one of the arguments planetary scientists use when making the case for a dedicated Neptune mission to space agencies and funding committees. The scientific return is not limited to Neptune itself. Every answer from a Neptune probe upgrades the understanding of ice giants everywhere. And there is a second argument that is harder to ignore. Neptune's internal heat generation, its atmospheric chemistry, and the speed at which its conditions are changing all raise questions that directly connect to the study of planetary habitability. Scientists trying to understand which kinds of planets can support life need to understand which kinds of atmospheric conditions are stable and which are prone to violent, rapid shifts. If ice giants can lose their cloud systems and flip their temperatures in a decade, that tells you something about the range of conditions life might need to survive in planetary systems built around multiple worlds. Neptune is not just a strange planet at the edge of our solar system. It is a data point in one of the largest questions in science. And the data point keeps changing. Measuring Neptune's temperature is harder than it sounds. The planet sits nearly 3 billion miles away. No thermometer reaches that far. No probe is currently orbiting it or flying through its atmosphere. Every temperature measurement humans have ever taken of Neptune came from telescopes pointing across an enormous gulf of space, trying to read energy signals too faint to see without the most sensitive instruments ever built. The method is called thermal infrared imaging. Every object with a temperature above absolute zero emits energy in the infrared part of the spectrum, which is invisible to the human eye, but detectable with the right instruments. By measuring the infrared light coming off Neptune's atmosphere, scientists can calculate the temperature of specific atmospheric layers. It sounds precise. In practice, it is full of complications. First, the signal is extremely weak. By the time infrared energy from Neptune's atmosphere crosses 3 billion miles of space and arrives at a telescope on Earth or in Earth's orbit, the signal has spread and weakened to an almost undetectable level. Measuring it accurately requires separating Neptune's infrared signature from the background noise of the universe, the constant faint glow of stars, galaxies, and the cosmic microwave background itself. Second, Neptune's atmosphere has multiple layers, and the infrared signal from each layer overlaps with the others. The signal scientists receive is a blended average of emissions from different depths, not a precise reading from a single altitude. Separating those layers requires computational models, and those models introduce their own sources of error. Third, there is the question of what is actually being measured. The temperature of a specific atmospheric layer on Neptune is not a single fixed number. It varies across the planet's surface, across different latitudes, across different times of day and night on Neptune, and across different seasons. Any single measurement captures a snapshot of a complex, variable system. Given all of these challenges, the accuracy of Neptune temperature readings carries a margin of error. Scientists acknowledge this. The 14-degree global cooling and the 20-degree South Pole spike are the reported values, but the actual numbers could be slightly different depending on which instruments were used and which models were applied. What researchers are confident about is the direction and the magnitude of the changes. Even accounting for measurement uncertainty, a 14-degree drop is real. A 20-degree polar spike is real. The changes are large enough that measurement error does not change the conclusion. But the uncertainty in the exact numbers means scientists argue about the specific causes. Two researchers looking at the same temperature data and the same atmospheric models can reach different conclusions about what is driving the changes, because the data leaves enough room for multiple interpretations. This is a fundamental challenge of observing distant planets. The further the object, the less precise the data, the more room for competing explanations. A probe inside Neptune's atmosphere would change that immediately. Direct temperature measurements from inside the clouds, at multiple altitudes, taken continuously over hours, would collapse the range of possible interpretations and give researchers the clean data they need to settle the debate. Every measurement taken from 3 billion miles away is a guess that gets better with better telescopes. But every measurement taken from inside the planet is ground truth. The difference between those two things is the difference between watching a patient from outside a hospital window and actually taking their vitals. And Neptune has been running a fever for over 2 decades. Nobody has been inside yet to take the reading directly. That changes what the next step in this story looks like. There is a spacecraft on a drawing board somewhere that could answer every question this video has raised. It just has not been built yet. Scientists and engineers at major space agencies have spent years designing what a Neptune mission would need to look like. The requirements are known. The physics is understood. The technology, in most cases, already exists in some form. What the mission currently lacks is funding and a launch date. Here is what the ideal mission looks like. First, an orbiter, a spacecraft large enough to carry a full suite of scientific instruments, capable of surviving the radiation environment of the outer solar system, and equipped to settle into a stable orbit around Neptune for at least 4 years. The orbiter would map the planet's atmosphere continuously, track storm formation and evolution in real time, measure temperature variations across the entire surface, and study the interior using gravity measurements and magnetic field data. 4 years of orbital data from Neptune would produce more scientific information about the planet than everything humanity has collected since its discovery in 1846. Second, an atmospheric probe, a smaller spacecraft released from the orbiter that dives directly into Neptune's atmosphere, transmitting data as it descends. The probe would not survive. The pressure and temperature increase so rapidly during descent that even heavily armored hardware would be crushed within roughly an hour of entry. But in that hour, the probe would record direct temperature readings, chemical composition at multiple altitudes, wind speeds, and direction at different layers, and the physical properties of the cloud particles. 1 hour of data from inside Neptune's atmosphere would resolve debates that have been running for decades. The journey to Neptune takes approximately 10 to 12 years with current propulsion technology, using gravity assists from Jupiter or Saturn to build up enough speed. A spacecraft launched in the late 2020s would arrive in the late 2030s. By that point, astronomers watching from Earth will have accumulated another decade of anomalous data to compare against. The scientific case for the mission is not in question. Every major review of planetary science priorities in the last decade has placed Neptune high on the list. The most recent decadal survey, published by the National Academies of Sciences in 2023, ranked a Uranus orbiter and probe as the top priority for large planetary missions. with explicit recognition that ice giant science is severely underfunded given how important these planets are. The recommendation was there. The funding has been slow to follow. Part of the difficulty is the timeline. Politicians and funding agencies work on cycles of months to a few years. A mission whose results arrive in 2040 or beyond requires sustained commitment across multiple administrations, multiple budget cycles, and multiple generations of agency leadership. Maintaining that commitment is one of the most persistent challenges in planetary science, and every year the launch slips is another year Neptune changes without witnesses. The planet is running its own experiment right now. Temperature changes happening, cloud chemistry shifting, storms forming and dying, dark particles appearing and evolving, and the only instruments watching are the same ground-based and orbiting telescopes that have been doing their best from 3 billion miles away. The scientists who study Neptune are patient people. They have to be, given what they study. But the patience is wearing thin, because the data from those distant telescopes has started suggesting something that makes even the most measured researchers pause. Something about the rate of change on Neptune, the speed and scale of the anomalies, that does not match any natural planetary cycle they have ever observed. Numbers can be boring. This one is not. When scientists measure change on a planet, they compare the rate of that change against what the planet's size, age, and energy input would predict. A planet Neptune's age, roughly 4.5 billion years old, should be changing slowly. Enormous planetary systems carry so much mass and so much thermal inertia that significant atmospheric shifts typically unfold over millions of years, not decades. Neptune's recent changes unfolded over 15 years. To understand how strange that is, imagine a boulder the size of a football stadium sitting on flat ground. Getting that boulder to move requires a genuinely massive force. Once it is moving, stopping it requires an equally massive force. The momentum of an object that large makes rapid changes in direction nearly impossible. Neptune's atmosphere is that boulder, except instead of a stadium, picture something the size of Earth multiplied by 17. That is Neptune's volume. An atmosphere wrapped around a planet that large carries inertia on a scale that should resist rapid change the way a mountain resists a light breeze. And yet the temperature swung 14 degrees in 15 years. The South Pole jumped 20 degrees in 2. Planetary scientists ran those numbers through their models, and the models struggled. The timescale was wrong. Changes of that magnitude, on a planet that massive, should require either an external event of enormous power, something like a major impact or a significant change in solar output, or an internal reorganization that had been building across millions of years and finally reached a tipping point. There was no major impact. Solar output changed during this period, but only within the small oscillations of the 11-year solar cycle, changes far too modest to drive atmospheric swings of this size. That leaves the internal tipping point hypothesis. Something inside Neptune, something that had been slowly building pressure or heat or structural change across a very long time, crossed a threshold around 2003 and started releasing that built-up energy through the atmosphere above. The changes humans have been measuring since then could be the visible surface expression of a slow interior process finally breaking through. If that is right, the changes are not random. They are the output of a process with its own internal logic, and that process may continue, escalating as more of the built-up energy releases, until Neptune reaches a new equilibrium. What that equilibrium looks like is unknown. Scientists cannot run a simulation accurate enough to predict it because the model of Neptune's interior is not detailed enough. The key variables, how heat moves through subaryonic layers, how chemical reactions proceed under extreme pressure, how the magnetic field interacts with the atmosphere, are all estimated rather than measured. Each of those estimates carries error, and when you multiply errors across a model that complex, the predictions for something as specific as a tipping point become very wide ranges. The honest scientific position is this: something changed inside Neptune around the early 2000s. That change is pushing the atmosphere into new territory, and nobody knows yet whether it is temporary or permanent. What happened next in the telescope data made temporary seem less likely. Neptune has a magnetic field, and it is one of the strangest in the solar system. On Earth, the magnetic field is tilted about 11 degrees from the planet's rotation axis. That means the North Magnetic Pole sits relatively close to the geographic North Pole. The two are not perfectly aligned, but they are close enough that a compass works reliably. The field itself is generated by the churning of molten iron in Earth's outer core, a process called a dynamo. Neptune's magnetic field is tilted by 47 degrees from its rotation axis, and the center of the field is not even at the planet's core. It is offset by about 55% of Neptune's radius, sitting much closer to the surface than the center. This is deeply unusual. Most planetary magnetic fields are roughly dipolar, with a north magnetic pole and a south magnetic pole positioned more or less symmetrically. Neptune's field is so off-center and so heavily tilted that it looks almost random compared to what standard planetary magnetic theory predicts. The likely cause is where Neptune's dynamo operates. Instead of a metallic core generating the field, Neptune's magnetic field appears to come from its middle layers, the supraionic water and ammonia region that sits between the deep interior and the outer atmosphere. That region conducts electricity well enough to sustain a dynamo, but because it is a shell rather than a core, the resulting magnetic field has a chaotic, multipolar shape. This matters enormously for understanding what is happening in Neptune's atmosphere right now. The magnetic field shapes how charged particles from the Sun interact with the planet. It controls where solar wind energy enters the atmosphere, which affects heating patterns at specific latitudes. It influences how certain chemical reactions proceed in the upper atmosphere, because some reactions are sensitive to electromagnetic conditions. A magnetic field generated in the chaotic supraionic middle layers of Neptune would be expected to shift and fluctuate as those layers change their circulation patterns. And if the internal processes scientists believe are currently active inside Neptune are actually reshaping the supraionic layers, the magnetic field itself could be changing. A changing magnetic field means changing patterns of solar wind interaction. Changing patterns of solar wind interaction mean new heating zones and new chemical activity in the atmosphere. Some researchers have proposed that a shift in Neptune's magnetic field geometry could be contributing to the atmospheric anomalies visible from Earth, adding another invisible force to the already complex picture. Detecting changes in Neptune's magnetic field from Earth is nearly impossible. The signal is too faint across 3 billion miles of space. Voyager 2 took direct measurements in 1989, and those measurements remain the only close-range magnetic data humanity has ever collected from Neptune, 35 years old, from a 5-hour flyby. On a planet that is currently in the middle of unprecedented atmospheric changes, the magnetic field could have shifted significantly since then, and no instrument would catch it from this distance. Only a dedicated orbiter carrying magnetometer equipment circling Neptune for years could map how the field currently looks and whether it is changing over time. That orbiter does not exist yet, and while scientists work with the data they have, Neptune keeps generating new phenomena that none of the existing measurements can fully explain. The latest involves something subtle, easy to miss in a single observation, but deeply significant when you see it repeated across years of data. Neptune has been in the same season for your entire lifetime, and it will stay in that season for years after you are gone. A single Neptunian season lasts over 40 Earth years. The planet's orbit is so enormous, taking 165 Earth years to complete, that even dividing that orbit into 4 seasons still produces timescales that dwarf any human life experience. If you were born at the start of a Neptunian winter, you would need to live well past 80 years old just to watch spring begin. This extreme timescale creates a scientific challenge with no easy solution. To understand Neptune's seasonal cycle fully, you need observations spread across a complete orbit. Humanity discovered Neptune in 1846. That means scientists have watched the planet complete exactly one full trip around the Sun, one orbit, one dataset. Every pattern, every anomaly, every theory about Neptune's behavior is built on observations from a single planetary year. For a planet this slowly evolving, that is like trying to understand Earth's entire climate system from a single year of weather data. The southern summer that is currently underway on Neptune began around 2005. Scientists know this because they can calculate Neptune's orbital position precisely. The southern hemisphere has been tilted toward the Sun, and by the physics of seasons, it should be receiving its peak solar energy input. The atmosphere responded by getting colder globally and then spiking violently at the South Pole specifically. The expected gradual warming never arrived. This is where the seasonal context makes things stranger. If the current anomalies are being driven partly by the seasonal cycle, perhaps the southern summer is producing effects that only appear once every 40 years. Then astronomers from 1846 to 2005 simply never had the instruments or the long-term monitoring programs to observe this same set of events during the previous summer. Maybe this happens every 40 years and nobody was watching carefully enough before. Or maybe this is the first time. Separating those two possibilities requires either waiting 4 more decades for the next southern summer or finding a way to read the historical record of the planet, signatures embedded in Neptune's geology or chemistry that record what happened during previous seasons. Planetary scientists call this paleoclimatology, the science of reading a planet's past climate from physical clues left behind. On Earth, ice cores, tree rings, and ocean sediments record centuries of climate history. On Neptune, such a record might exist in the chemical layering of the atmosphere, in isotope ratios within different gas species, in patterns of cloud-forming compounds that accumulated over millions of years. Extracting that record requires either the orbital probe that does not exist yet, or breakthrough capabilities in spectroscopic analysis from Earth-based telescopes that are currently being developed. Both paths lead to the same conclusion. Understanding Neptune's seasonal behavior requires a long-term commitment to watching and measuring a planet whose timescales dwarf the career of any individual scientist. And that patient, decades-long watching is starting to reveal something about how Neptune compares to another ice giant much closer in the solar system, one that scientists assumed they understood better. Neptune and Uranus are often grouped together as the solar system's ice giants, treated as a matched pair. The pairing is technically accurate and practically misleading. The two planets share a size category and a basic chemical makeup. Both have thick atmospheres rich in methane, water ice, and ammonia. Both are far smaller than Jupiter and Saturn, but far larger than Earth. And both orbit in the cold outer reaches of the solar system, where sunlight is faint and temperatures are brutal. But their personalities could not be more different. Uranus is quiet, eerily, almost suspiciously quiet. Its atmosphere shows relatively little storm activity. Its temperature profile is close to what the models predict for a planet at that distance from the Sun. And most strangely, Uranus shows almost no internal heat generation. A planet formed from the same basic processes as Neptune, at roughly the same time and in roughly the same region of the early solar system, releases almost no excess heat from its interior. Neptune is the opposite. Active, turbulent, changing rapidly, and pumping significant excess heat through its atmosphere from a deep internal source. Why two planets of the same category, the same age, and similar compositions behave so differently is one of the genuinely unsolved problems in planetary science. The leading hypothesis involves impacts during the early solar system. Both planets likely experienced collisions with large objects during the chaotic period of planetary formation. An impact powerful enough, striking at the right angle, could fundamentally alter a planet's internal structure, disrupting the heat-conducting layers and either accelerating or shutting down the internal dynamo. Uranus may have been hit in a way that disrupted its heat engine and left it running cold. Neptune may have escaped that fate, or been hit differently, leaving its internal heat source intact and active. This matters for the current Neptune mystery, because if the internal heat source is the driver of all the recent atmospheric anomalies, understanding why Neptune has it and Uranus does not might reveal exactly what is happening deep inside Neptune right now. The contrast between the two planets also highlights how poorly ice giant physics is understood. Two objects in the same category, separated by about 1 billion miles in the outer solar system, with completely different internal energy outputs and completely different atmospheric behaviors. The models that should apply to both of them equally fail to capture what actually makes them different. Scientists building models of ice giants in other solar systems have to navigate this problem constantly. When observing a distant ice giant with a telescope, they cannot tell from the data alone whether the planet is a quiet Uranus type or an active Neptune type. The difference has enormous implications for that planet's weather, its chemistry, and potentially its ability to support conditions relevant to life. Neptune is teaching scientists that the ice giant category is far broader and more variable than previously thought. And everything that makes Neptune currently unique and surprising may turn out to be the norm for ice giants across the galaxy. That means the panic scientists are feeling about Neptune has implications stretching far beyond this solar system. Science does not often engage the sense of smell. On Neptune, it becomes impossible to ignore. Neptune's atmosphere carries a chemical called hydrogen sulfide. This is the compound responsible for the smell of rotten eggs. It is present in Earth's volcanic gases and in the decomposition of organic material. The smell is so sharp and distinct that humans can detect it at extremely low concentrations. On Neptune, hydrogen sulfide exists in substantial quantities, mixed through the atmosphere, and concentrated especially in the deeper, higher pressure layers. The dark vortices, which appear to draw material upward from those deeper layers, bring hydrogen sulfide with them as they rise. The storm systems on Neptune almost certainly carry a powerful and overwhelming rotten egg smell. For scientists, the smell is incidental. What matters is what hydrogen sulfide reveals about the planet's chemistry and the internal processes driving the storms. Hydrogen sulfide forms at specific temperatures and pressures. Finding it at particular altitudes tells scientists something about the temperature and pressure conditions at those depths, and about how efficiently the vortex is lifting material from below. Tracking the concentration of hydrogen sulfide in different parts of the atmosphere at different altitudes and latitudes would give researchers a tracer for vertical movement, a way to see where the atmosphere is turning over and where deep material is surfacing. The recent observations of dark spots have included spectroscopic readings suggesting elevated hydrogen sulfide concentrations inside the vortex structures. This is consistent with the idea that the dark material inside the spots contains hydrogen sulfide ice particles lifted from deep inside the planet and frozen into the upper atmospheric layers by the storm's dynamics. But hydrogen sulfide at high altitude is unstable. Ultraviolet radiation from the sun breaks it apart. In the upper atmosphere, molecules of hydrogen sulfide have a relatively short lifetime before photochemistry destroys them. The fact that hydrogen sulfide particles appear to be surviving inside the dark vortices suggests the interior of those storms shields the material from ultraviolet exposure. The spinning structure creates a protected environment where the chemistry that would normally be destroyed survives longer than it should. A storm system that protects unusual chemistry from the sun. Inside that protected zone, reactions proceed that could not happen anywhere else in the atmosphere. The dark vortex becomes a chemical laboratory unlike anything else on the planet. What those protected reactions produce, what compounds form inside the vortex that do not exist anywhere else on Neptune, is a question that cannot be answered from 3 billion miles away. Direct sampling would require flying directly into one of those storms. Which brings the question of a probe back to the center of the conversation, and with it, a specific engineering problem that has challenged mission designers for years. Getting a probe safely into Neptune's atmosphere is harder than it sounds, and the reason involves a number that stops most conversations cold. A spacecraft entering Neptune's atmosphere would face conditions that make the bottom of Earth's ocean feel comfortable. Start with the entry phase. A probe approaching Neptune from orbit would hit the outer atmosphere at roughly 17 miles per second. That is about 60,000 miles per hour. The friction between the spacecraft and the atmospheric gas at that speed would generate temperatures on the heat shield approaching 27,000 degrees Fahrenheit. That is more than 4 times hotter than the surface of the sun. The heat shield would need to absorb and deflect that energy without transferring it to the interior of the spacecraft. Heat shield technology, capable of handling those temperatures, exists, developed through decades of atmospheric entry missions. But Neptune's higher gravity and denser atmosphere make the entry more violent than anything humans have tested hardware against in an actual planetary atmosphere. If the heat shield performs correctly, the probe survives the initial violent plunge and deploys its parachute or descent system. Now it begins floating downward through the atmosphere, transmitting data back to the orbiter overhead, which relays the signal across nearly 3 billion miles to Earth. The wind is the next problem. Neptune's wind speeds near the top of the cloud layer exceed 1,000 miles per hour. A probe dropping through those wind layers would be thrown horizontally at speeds that make controlled descent extremely difficult. The transmission antenna needs to point toward the orbiter, while the probe is being thrown sideways at hurricane speeds, many times more powerful than any storm on Earth. As the probe descends deeper, pressure increases rapidly. Every mile of descent adds enormous pressure to the spacecraft's hull. The probe would need to withstand pressures roughly 10 times greater than what a submarine experiences at the deepest point of Earth's oceans. Temperature also increases with depth. What started as an extremely cold environment near the cloud tops becomes progressively hotter as the probe descends toward the lower atmospheric layers, where internal heat from the planet's interior is closer to the surface. Most mission designs estimate a functional lifetime of 45 minutes to 1 hour for the atmospheric probe before the combination of pressure, temperature, and wind damage ends transmission. That 1 hour is worth every engineering challenge required to achieve it. The data gathered during descent would tell scientists the exact temperature profile at every altitude, the chemical composition layer by layer, the wind speed and direction at multiple depths, and the physical properties of the cloud particles. This information, collected directly rather than inferred from distant observations, would immediately resolve most of the competing hypotheses about what is driving Neptune's behavior. 1 hour of data, collected by a spacecraft that will be destroyed in the process, in exchange for the answers to questions that have been building for decades. Mission engineers call this kind of sacrifice worthwhile. The probe is expendable, the data is not. And that data would do more than explain Neptune. It would recalibrate the models used to study ice giants across the galaxy, giving astronomers better tools for understanding the most common type of planet in the universe. The scientific return on that 1 hour would echo through planetary science for generations. Every time a telescope points at a distant solar system and spots an ice giant orbiting another star, scientists are making assumptions. Assumptions about that planet's atmosphere, temperature, internal structure, and weather. Those assumptions are built on models, and those models are built substantially on what we know about Neptune. The exoplanet field has grown enormously in the past 20 years. Telescopes like Kepler and its successors have identified thousands of planets orbiting other stars. A significant portion of those planets fall into the ice giant size range, larger than Earth but smaller than Jupiter. Scientists call them super Neptunes or mini Neptunes depending on their exact size, and they appear with remarkable frequency across every stellar neighborhood astronomers have surveyed. To characterize these distant worlds, scientists need to know what their atmospheres are doing, how their temperatures distribute, whether they have cloud systems, and what drives their weather. All of that analysis relies on atmospheric and interior models, and the most directly tested version of those models is the one applied to Neptune. If Neptune's models are failing, which the data since 2003 strongly suggests, then the conclusions drawn about thousands of distant ice giants need to be reconsidered. This is a significant problem. Some of those exoplanet ice giants orbit in the habitable zones of their stars, the region where liquid water could theoretically exist on a planetary surface. Determining whether a planet in the habitable zone is actually hospitable to life requires knowing whether its atmosphere is stable, whether its temperature swings are manageable, and whether its internal processes support or destroy surface conditions. All of those determinations go through models that Neptune is currently breaking. Scientists studying habitability around other stars have started incorporating the Neptune anomalies into their frameworks, but the revisions are limited by the same problem affecting every other field of Neptune research. There is not enough direct data to know which parts of the model are wrong and by how much. Neptune is sitting at the center of multiple major scientific questions simultaneously: planetary formation, ice giant physics, atmospheric chemistry, interior dynamics, and now, through the exoplanet connection, the question of where life might exist in the galaxy. One planet, 4.5 billion years old, 3 billion miles away, currently changing in ways nobody predicted, and yet the scientific community's ability to study it remains severely limited by the absence of a dedicated mission. Some researchers have pointed to this situation as one of the clearest examples of a gap between scientific priority and scientific funding in the history of space exploration. The need is documented. The tools exist or are buildable. The scientific return is enormous. The mission remains unfunded. What would shift the equation? Some scientists believe a specific discovery, something visual and undeniable captured by ground-based telescopes, could change the political calculus around a Neptune mission, the way that early Mars images changed public enthusiasm for Mars exploration. Neptune has been providing dramatic data for 20 years. Whether that data reaches the right audience, whether it creates the kind of public and political pressure that moves a mission from wish list to launchpad, depends on something science cannot fully control. It depends on people paying attention. Every measurement humans have of Neptune's atmosphere came from light, visible light showing cloud structures and storm positions, infrared light revealing temperature patterns, ultraviolet light measuring chemical reactions in the upper atmosphere. Each wavelength of light carries a different kind of information, and each one adds a piece to the picture. Scientists call the technique spectroscopy. By splitting the light from a distant planet into its individual color components, they can identify which chemicals are present in the atmosphere. Every chemical element and compound absorbs and emits light at specific, unique wavelengths, like a fingerprint. Matching those fingerprints in the incoming light from Neptune against a database of known chemical signatures lets researchers map the planet's composition without ever sending a spacecraft. This is the primary tool scientists use to track Neptune's temperature changes, cloud disappearance, and the chemical signatures inside the dark spots. The tool is powerful. It is also limited. Spectroscopy from Earth or from an orbiting telescope like Hubble gives scientists averaged information across the visible face of the planet. The signal coming back from Neptune is a blend of light from millions of square miles of atmosphere compressed into a single reading. Separating that blend into information about specific locations, specific altitudes, or specific storm systems requires sophisticated data processing and introduces additional uncertainty. The spatial resolution available from Earth, meaning how small a detail we can see on Neptune, is roughly comparable to trying to read the label on a bottle from across a football field. In perfect conditions, you might make out large text. Fine print is impossible. This limitation explains why the dark spots, which are thousands of miles across, are visible, while smaller features and subtle chemical variations remain hidden. The planet is always partially obscured by the sheer distance between us and it. Adaptive optics technology has improved this situation significantly. Ground-based telescopes, equipped with adaptive optics systems, can partially compensate for the distortion that Earth's atmosphere creates, producing sharper images of distant planets. The Very Large Telescope in Chile, which has been one of the primary instruments studying Neptune's recent anomalies, uses adaptive optics to achieve resolution that would have been impossible 20 years ago. The James Webb Space Telescope, launched in 2021, brought infrared sensitivity far beyond anything previously available. Early Webb observations of Neptune produced the sharpest infrared images of the planet ever taken, revealing atmospheric structures and temperature patterns invisible to previous instruments. Webb data is now being incorporated into the models scientists use to interpret Neptune's behavior. The additional infrared detail is helping researchers refine temperature estimates and chemical composition readings. Every improvement in data quality narrows the range of possible explanations for what is happening. But even Webb, the most powerful space telescope humanity has ever launched, is observing from Earth's orbit. The fundamental limitation of distance remains. The light carrying Neptune's secrets still has to travel nearly 3 billion miles before Webb can collect it. All of the improvements in telescope technology are closing the gap. They are not eliminating it. And the most critical information about Neptune's interior, the region that appears to be driving everything visible at the surface, cannot be accessed by any telescope from any distance. It is buried under thousands of miles of crushing atmospheric pressure and layered chemistry, waiting to be measured directly. And what might be hiding in those deep layers, based on what scientists currently suspect, is something that changes the way you think about ice giants entirely. Deep inside Neptune, it may be raining diamonds. This idea started as a theory and has been moving toward confirmation through a series of increasingly convincing experiments. Understanding it requires going far below the atmospheric layers scientists can observe from Earth, down into the interior, where pressure and temperature reach levels that do not exist anywhere on the surface of any planet humans have ever visited. At depths of several thousand miles inside Neptune, the pressure is roughly 2 million times greater than the atmospheric pressure on Earth's surface. Temperatures reach thousands of degrees Fahrenheit. Under those conditions, the methane gas that colors Neptune's atmosphere behaves in a completely different way. Methane is a simple molecule, one carbon atom bonded to 4 hydrogen atoms. Under extreme pressure, those bonds break. The hydrogen atoms separate and float away into the surrounding gas. The carbon atoms, suddenly free and under enormous compression, begin bonding with each other. Carbon under extreme pressure and heat forms one specific structure, diamond. The carbon atoms crystallize. They form microscopic diamonds, tiny crystals of pure carbon, in the deep interior of the planet. Those crystals are denser than the surrounding liquid material, so they sink. They fall downward toward Neptune's core, continuing to grow as they accumulate more carbon along the way. Scientists at Stanford University and other research institutions have reproduced this process in the laboratory, using powerful laser pulses to create extreme pressures for brief moments. In those experiments, carbon atoms from methane molecules formed diamonds under the pressure conditions that match Neptune's interior. The experiment worked. The diamonds do not just fall harmlessly. As they sink, they displace material around them. Denser material sinking and lighter material rising creates convection currents, the same kind of circular movement that happens when warm water rises and cold water sinks. Those convection currents carry heat upward through Neptune's interior, contributing to the excess heat the planet radiates at the surface. A diamond rain, falling through the planet's interior, is potentially part of the engine powering Neptune's excess heat generation. And here is where this connects to the current anomalies. If the rate of diamond formation changes, perhaps because the chemical composition of Neptune's interior is shifting, or because temperature and pressure profiles in the middle layers are evolving, the rate of heat transport through the interior would change with it. A shift in how efficiently diamonds form and fall could alter how much heat reaches the atmosphere. It could change temperature distributions at the surface. It could amplify or suppress the atmospheric processes that create clouds, storms, and the polar heating event. The diamond rain is not just a beautiful idea, it may be a mechanism, a hidden gear in the engine that is driving everything scientists have been watching since 2003. And if the gear is changing speed, the engine outputs differently. The atmosphere changes, the clouds respond, the storms behave in new ways. A planet changing because it is slowly raining diamonds through itself from the inside out. Single events on planets are manageable. Scientists observe them, measure them, build models around them, and eventually explain them. Feedback loops are different. A feedback loop happens when an event causes a change that causes more of the original event. Heat escapes from Neptune's interior through a dark vortex. The vortex warms the surrounding atmosphere. Warm atmosphere rises and creates more instability. More instability generates more vortices. More vortices allow more heat to escape. Each step makes the next step bigger. Scientists observing Neptune's recent behavior have identified several potential feedback mechanisms operating simultaneously, and the interaction between them is where the real complexity lives. The first potential loop involves the cloud chemistry. The sun's ultraviolet light drives photochemical reactions that build Neptune's clouds. Those clouds reflect sunlight back into space, which affects how much energy the atmosphere absorbs. Fewer clouds means more solar energy absorbed at lower atmospheric levels, which changes the temperature profile, which affects the photochemical reactions, which affects the next generation of cloud formation. This loop could be running in either direction. A disruption that removes clouds allows more energy in, which changes the conditions for clouds to form again. Whether the system settles back to the original cloud coverage, finds a new equilibrium at lower cloud coverage, or oscillates between the two states depends on the specific balance of the reactions involved. The second potential loop connects internal heat to storm activity. As described in the context of the dark vortices, storms may create channels for internal heat to escape more efficiently. More heat escaping creates more atmospheric instability. More instability generates more storms. More storms open more channels. This loop could be self-amplifying under the right conditions, meaning Neptune's storm activity could increase on its own, driven by a process that generates more of itself. The third potential loop involves the magnetic field. If the internal process is changing, Neptune's atmosphere are also shifting the superionic layers that generate the magnetic field. The resulting changes in the magnetic field alter how solar wind energy interacts with the upper atmosphere. Changes in that interaction affect upper atmospheric heating, which affects the photochemical cloud reactions, which loops back into the first feedback mechanism. 3 interconnected loops, each one capable of amplifying the others. Climate scientists on Earth study feedback loops constantly because they are central to understanding how Earth's climate changes. The concern with feedback loops is that they can push a system past a tipping point, a threshold beyond which the original conditions cannot be recovered. Past that point, the system moves toward a new state and stays there. Scientists watching Neptune's anomalies are asking whether the planet is approaching or has already passed a tipping point of its own. The rate of change, the simultaneity of multiple atmospheric shifts, and the apparent connection between surface behavior and deep interior processes all suggest a system under significant internal pressure. Whether that pressure resolves gently or dramatically is something current instruments cannot determine. What is knowable is that the longer these feedback loops run unchecked, the further the planet moves from the conditions Voyager observed in 1989, and the further it moves, the less the old models apply. A new Neptune is emerging. Scientists are watching it form in real time. A planet 3 billion miles away is trying to tell us something about our own atmosphere. Scientists are starting to listen. The connection is not obvious. Neptune and Earth are profoundly different objects, different sizes, different compositions, different distances from the Sun, different histories. There is no direct comparison between what is happening in Neptune's methane and hydrogen atmosphere and what happens in Earth's nitrogen and oxygen atmosphere. The connection runs through the science itself. Atmospheric physics is governed by equations that apply to all planets. The same mathematical tools that describe how heat moves through Neptune's layers describe how heat moves through Earth's layers. The same equations that model cloud formation in hydrogen sulfide and methane atmospheres are derived from the same underlying principles as the equations for water vapor clouds on Earth. When those equations fail on Neptune, scientists have to ask whether the failures reveal flaws in the equations themselves or flaws in the assumptions built into how the equations are applied. Neptune's 14-degree temperature drop, despite increased solar input, challenged a basic assumption that increased solar energy input always correlates with increased atmospheric temperature. On Earth, this assumption underlies much of climate modeling. If a planet can receive more solar energy and get colder because of internal chemical and dynamic processes that counteract the solar input, that is a reminder that planetary atmospheres are not simple systems where one input produces one predictable output. The lesson is not that Earth's climate models are wrong. They are built on vastly more data, validated against centuries of direct observation, and tested constantly against real-world measurements. The lesson is about humility in modeling complex systems. Neptune's atmosphere surprised scientists who thought they understood it. The surprise came from processes operating below the visible surface, in the interior and in the deep chemistry, that the models did not adequately represent because there was no direct data to build them from. Earth's atmosphere also has processes operating below the visible surface: ocean heat circulation, deep geological heat release, chemical reactions in the lower atmosphere and at the ocean-atmosphere boundary. Most of these are reasonably well measured, but the history of Earth climate science is also a history of surprises, of processes that turned out to be more important than expected or that operated differently than models predicted. Neptune is a reminder that surprises happen, that complex systems can shift faster than expected, that the visible surface behavior of a planetary atmosphere can be driven by invisible processes deep inside the planet that standard observations never reach. And if there is one message that transfers directly from Neptune to Earth, it is this: the interior matters, the deep processes matter, the systems connecting the surface to the depths matter. Understanding a planet requires understanding all of it, not just the part visible from outside. 20 years ago, Neptune was a known quantity. Scientists had Voyager's 1989 flyby data, decades of ground-based telescope observations, and a model that seemed to work. The planet was cold, distant, slowly changing, and largely predictable. It fit into the framework of solar system science without causing major disruptions. Then the temperature monitoring started. The anomalies accumulated. The models failed one after another. And by 2023, Neptune had become the most scientifically discussed planet in the outer solar system for all the wrong reasons. Each year brought a new discovery. 2003 brought the temperature monitoring data, revealing the beginning of the global cooling. 2015 brought the reversing dark vortex spotted by Hubble. 2018 brought the stratospheric temperature minimum and the South Pole spike. 2019 brought the cloud disappearance. 2020 brought confirmation of the polar temperature surge. 2023 brought the first published analysis connecting cloud loss to the solar cycle and the first public suggestion that multiple feedback mechanisms might be operating simultaneously. The pace of discovery accelerated because the observational campaigns accelerated. As the anomalies mounted, more telescope time was dedicated to Neptune. More researchers joined the effort. More data arrived. And as the data piled up, a consensus began forming around a deeply uncomfortable conclusion. Neptune was changing in ways that exceeded the explanatory capacity of existing models. The models were not slightly wrong. They were missing something fundamental about how ice giants work. That conclusion had ripple effects across planetary science. It prompted new theoretical work on superionic layers and internal heat transport. It generated new proposals for adaptive optics campaigns using the Very Large Telescope. It pushed the James Webb Space Telescope team to prioritize Neptune observations and publish early results. It strengthened the case for a dedicated ice giant mission in the Planetary Science Decadal Survey. The Decade of Anomalies did not just change understanding of Neptune, it changed the direction of outer solar system science, and it changed the conversation about what a solar system is, not a static collection of objects moving in predictable orbits, each one settled into its permanent character, but a dynamic system where planets can surprise you, where interiors can drive surfaces, where a distant sun can reach across billions of miles and switch a cloud system on and off, and where the things humans thought they understood the best sometimes turn out to be the most mysterious. Neptune spent 4.5 billion years orbiting quietly. Then, on a timescale that humans could observe, it started changing. The question that planetary scientists now carry into every new observation session is a simple one. Is Neptune finished changing? Or is this just the beginning? Neptune does not do ordinary. Every major measurement scientists have taken of the planet since 2003 has set a record, the largest temperature drop ever recorded on an outer solar system planet, the fastest polar temperature spike ever recorded on any planet, the first complete disappearance of a planetary cloud system in recorded history, the first observed reversal of a continent-sized storm, the first documented simultaneous appearance of paired dark and bright vortices on opposite hemispheres, record after record, all from the same planet, all within 20 years. In sports, an athlete who keeps breaking records is celebrated as extraordinary. In science, a planet that keeps breaking records is a warning that the underlying understanding is insufficient. Every record Neptune sets is a data point that falls outside the distribution scientists expected. One outlier can be a fluke. 2 outliers prompt a closer look. 6 outliers across multiple independent measurements, spanning 2 decades, all pointing toward the same conclusion that the models are missing something, constitute a scientific crisis. The crisis is productive. Science progresses through exactly this kind of confrontation between data and theory. When data wins the confrontation, theories improve. New models get built that can accommodate the observations. Understanding advances. But the process requires data. And for Neptune, the most important data still does not exist. Scientists have no direct measurements of Neptune's deep atmosphere, no direct readings of the interior temperature or pressure profiles, no direct chemical sampling of what is happening below the cloud layer, no direct magnetic field measurements from orbit. Every record Neptune has set has been documented from 3 billion miles away, through the blurred lens of distance, with all the uncertainty that entails. The records are real. The causes behind them remain contested. What scientists are converging on is a picture of Neptune as a coupled system, a planet where the deep interior, the middle atmospheric layers, the upper atmosphere, and the external forcing from the sun are all connected to each other in ways that amplify small changes into large effects. A small shift in the interior becomes a large shift at the surface. A small change in solar output removes an entire cloud system. A coupled system is sensitive. Sensitive systems break records more often because inputs do not stay local. They propagate. Neptune may be one of the most sensitive planetary systems in the solar system. Its isolation, its extreme distance from the sun, its unusual magnetic field, its violent winds, and its active interior all combine to create a world where small causes produce enormous effect. And the most extreme effect of all, the one scientists are still waiting and watching for, has not arrived yet. The data has been building for 20 years. The models are behind. The mission is unfunded, and Neptune is still changing. Researchers who study the planet disagree on many things. They disagree about which internal process is the primary driver of the anomalies. They disagree about how much of the cloud loss is driven by the solar cycle versus internal dynamics. They disagree about whether the feedback loops they have identified are stabilizing or self-amplifying. What they largely agree on is this: The changes are ongoing. Neptune has not settled into a new equilibrium. The planet is still in motion. Several scenarios are considered plausible within the scientific community. The most optimistic scenario involves a natural recovery. The solar cycle continues its upward trend toward maximum activity. Ultraviolet output increases, photochemical cloud reactions restart, and Neptune's cloud coverage gradually rebuilds over the next few years. The temperature anomalies, driven partly by the same solar cycle and partly by internal processes that have already peaked, begin to moderate. The planet moves toward a new state that is different from Voyager's Neptune but stable. A more concerning scenario involves the feedback loops sustaining themselves. The dark vortex activity keeps opening channels for internal heat. The heat keeps driving atmospheric instability. The instability keeps generating new storms. The planet's temperature distribution remains irregular, with some regions much warmer than expected and others much colder. The cloud system returns partially, but never fully recovers. Neptune stabilizes in a state of chronic turbulence, fundamentally different from anything previously observed. The most extreme scenario, considered less likely but not impossible, involves the anomalies representing the early stages of a much larger and slower transition in Neptune's interior structure. A reorganization of the superionic layers, playing out across centuries, that would progressively alter the planet's heat output, magnetic field, and atmospheric chemistry in ways that accumulate over timescales far longer than human civilization has existed. No telescope from Earth can distinguish between these scenarios with certainty. The data is not precise enough. The models are not complete enough. The baseline record of a single completed Neptune orbit is not long enough to place the current changes in their full context. And yet, scientists keep watching. They keep refining the models. They keep making the case for a mission that could resolve the uncertainty in a way nothing else can. Because what is happening on Neptune right now, whatever it turns out to be, is telling us something about how planets work that no previous observation in the history of astronomy has revealed. Behind every telescope pointed at Neptune is a person, a researcher who chose to dedicate years of their career to a planet most people cannot name, that exists as a faint blue dot, even through the most powerful ground-based telescopes, and that has not been visited by any spacecraft in over 35 years. These scientists submit telescope time proposals, compete for observation slots, process data in the middle of the night, and write papers that a small community of specialists read carefully and debate in detail. They present at conferences, they argue about models, they revise their estimates, and submit new proposals the following year. It is slow work, patient work, work that produces rewards measured not in days or months, but in decades. And then Neptune started changing faster than any of them expected. The past 20 years have been strange for the researchers who study the outer solar system. They went into their field knowing it would be quiet, knowing the planets moved slowly, changed slowly, revealed themselves slowly. The pace of discovery in outer solar system science was expected to match the pace of the planets themselves. Instead, the data started coming in faster than the explanations. Anomaly after anomaly, each one requiring new modeling, new theoretical work, new conversations with colleagues in different specialties. Atmospheric chemists needed to talk to interior physicists. Interior physicists needed to talk to solar cycle experts. Solar cycle experts needed to talk to exoplanet researchers. Neptune forced a collaboration across subfields that rarely communicated before, and that collaboration has already produced new science. New models of photochemical cloud formation that incorporate solar cycle variability more precisely. New theories of heat transport through superionic planetary layers. New frameworks for connecting magnetic field behavior to atmospheric dynamics. Neptune broke the models. The researchers who study it are building better ones. Those better models will outlast this generation of scientists. They will be used by researchers who are currently in high school, people who will eventually propose and build and operate the mission to Neptune that has been in the planning stages for so long. Those future scientists will launch the mission, wait out the decade of travel time, and receive the first direct atmospheric data from inside Neptune's clouds. When that data arrives, they will compare it against the models built from the anomalies of the 2010s and 20s, and they will see how close the predictions came. Some predictions will be vindicated, others will be shattered by the direct measurements. Both outcomes advance the science. The scientists watching and waiting right now know they may not live to see the probe data arrive. They keep watching anyway, because understanding a planet does not require being the person who finally sends a spacecraft there. It requires being part of the long, collective, multi-generational effort that makes that spacecraft possible. And that effort, right now, is more urgent than it has ever been. Neptune is 3 billion miles away. It has no life on it. Its atmosphere would kill a human in seconds. Its storms would shred any structure we could build. Its temperature would freeze technology solid within minutes. It is as alien and hostile as anything in the known solar system, and it matters enormously. Science does not operate by studying only the things closest to home. The history of discovery is a history of looking further, asking harder questions, and accepting that answers to those questions change what is possible. Understanding electricity seemed abstract until it lit every city on Earth. Understanding the atom seemed academic until it powered submarines and hospitals. Understanding gravity seemed philosophical until it landed humans on the moon. Understanding ice giants is the current frontier of the same long chain. Neptune is showing scientists that planets can change faster than models predict, that internal processes can drive surface behavior in ways that external observation alone cannot capture, that the most common type of planet in the galaxy is also the least understood type of planet in our own solar system. Every conclusion scientists draw about whether a distant planet might support life, whether its atmosphere is stable, whether its climate could persist long enough for biology to develop, runs through the same models that Neptune is breaking right now. Fixing those models is not an abstract scientific exercise. It is the foundation of every future search for habitable worlds. And there is a more immediate reason this matters. Earth is a planet with an atmosphere. Earth's atmosphere is connected to its interior through volcanic activity, ocean heat exchange, and geological processes that operate below the surface. Earth's climate is influenced by the solar cycle. Earth has feedback loops that amplify or dampen climate changes. Every one of those statements is also true of Neptune. The physics is the same. The scales are different. The compositions are different. But the fundamental challenge of understanding how an atmosphere, an interior, and a star interact to produce a planet's climate is the same challenge on both worlds. Scientists who study Neptune are studying the general principles of how planets work. Those principles apply here too. Neptune started changing. The models failed. Scientists are working to understand why. That process, the confrontation between a surprising universe and the human determination to explain it, is exactly how science is supposed to work. It is how every major advance in understanding has ever happened. The planet 3 billion miles away is broken open, showing its interior in ways it never has before, asking questions that the best scientists on Earth cannot yet fully answer. The answers are coming. They always do. But first, someone has to build the spacecraft.